Okay. Okay, I think it's recording. Okay, it's a pleasure for me to introduce Alexander Bufetov. He's a director of research at CNRS in Marseille. He's also a member of the prestigious Stecklock Institute of Mathematics, and he's a recipient of many awards and author of many papers in top-ranking journals. So we will talk to us about determinantal point processes.
Okay, thank you very much. Okay, so I want to start with a very specific example. I want to start with a very specific example. So let us consider just unitary matrix. And let's consider, is it okay for references for Zoom? Yes, it's okay. Yeah. So, and let us consider just its spectrum. So, okay. So then the distribution of the eigenvalues of this unitary matrix. So on the unitary group, we have just hard measure. And the distribution of the eigenvalues is given by the following test. Is given by the following. So this is just the Weil character form. So the distribution is not uniform. In fact, there is this Vandermonde factor, and just which reflects the fact that eigenvalues don't like to be together. They repel each other. Okay, so now this can be written down as determinant just by writing this expression among the determinant and multiplying corresponding matrices. This can be written down as determinant K theta I. Theta J. Well, you see. Here I will chain, where K is in fact just the sign kernel of div shape, just the div shape. So, and it's small. Over 2 over this is just a result of opening out the Vandermonde determinant here. So let me do this just using Vandermonde determinant, multiplying and summing the geometric series. So the interesting fact about this formula is quite important for us, that the kernel K, the kernel Kn is kernel of
M is the same as their capital N.
Yes, thank you very much. Yes, thank you. So yes, so the
Sasha, can I make you a question?
Yes, yes, of course, please.
So U is an operator in the unitary space of dimension n.
That's right. Unitary matrix of unitary n times n unitary matrix. Yes.
Okay, the theta k and the eigenvalues.
Yes.
And what is the notation that you are using there of that product?
I'm not sure I understand the question.
So you have that notation down there that you are using.
This one, yes.
Yes.
It's just a measure. It's a measure.
A measure. Okay.
It's a measure. So it's the image again. I take the map. U goes to spectrum. So I have a hard measure here, and so it is moved. It is pushed forward to some measure, the image of our measure. I can value. So this is what I wrote.
Okay.
Yeah.
Thank you.
Okay. So it is important to keep in mind that this kernel, this expression, is in fact kernel of projection. So this is projection. So as the kernel is, this is projection just on n first harmonics, well, n first harmonics, in first place. So using the fact that this is projection, one is not difficult to prove the following very general proposition. It's in fact very general. So here, this measure is measured on some very high dimensional space. So n is maybe million. Yes? But I want to project this measure, let's say, on the first 3 points. And so the remarkable fact is that this determinantal structure is preserved by projection. Is preserved by projection. So projection.
So let me just
let me just finish the sentence, and I will answer it. Projection of this measure, of the measure onto the first m coordinates is, well, there is a constant depending on m, which we don't care about. Determinant k depending on m and determinant k n, the very same determinant, but now taken from ij from 1 to n. Here it was ij from 1 to ij from 1 to n. Here's from 1 to n. D theta I over 2. Yes, excuse me. By the way, I'm not ready to take questions.
so I was saying, so you are projecting onto the spectrum. So the spectrum can have repetitions, but
it's a set of measures here.
Okay, so
yes.
You are ignoring possible repetitions.
No, I'm not ignoring. It's part of the statement that is set of measures here.
I'm just trying to understand.
Yes. So I'm not ignoring. It's part of the statement. But as is clear from this, in fact, you can also see that it was a very important point. I will maybe not today, but I will, and maybe not today if we have time. We will discuss this in great detail. The fact is that close eigenvalues have extremely small probability. It's very improbable for eigenvalues because this will be a quite essential fact exploited a lot in this course.
Okay, but my second question is there a natural order?
This is an absolutely excellent and quite important question. So in fact, no, precisely. So precisely, this is very important. So when I say you're completely right, when I say first m coordinates, there are no natural coordinates.
Yes.
So in fact, it is more natural to consider this set not as a collection, not as a vector, but in fact as a subset of m elements, or we shall use the term configuration. Configuration is just a subset. Okay, now Of course, it doesn't matter in this case. You can number them in any way. There is a bijective correspondence between configurations and just vectors. It's clear. You take a vector, you forget the ordering. You take a configuration, you order it in any way. So you associate, in fact, not one vector, but m factorial vectors. But that's it. It doesn't matter. So this one is the reason why I don't want to write this constants.
The expression is permutation invariant.
Indeed. Everything is permutation invariant. Yes. You can see it. Yes, but my point is that what you ask is quite important because it will become very important when we pass to infinite configurations in a minute. So in fact, infinite configurations are indeed configurations. So, and even if, let's say, on the line, it is possible to number in increasing order, starting from zeros like this, already on the plane is much less clear and much less natural. And especially again, since closed particles are important, but however, for example, on the line, you can sort of number everything, and then adjacent particles will have close number. But on the plane, it will be quite difficult to number. So maybe you number, but maybe particle number 100 and number 1 million are in fact very close because you clockwise and then you return this. So I'm just trying to say it, you are absolutely right, and it's quite important for us that we are discussing not vectors but subsets. Okay? Does it make sense? Okay, perfect. I continue. Okay, so this is just the measure. So this determinantal property, this determinantal form of the density is preserved under projections. So please observe how remarkable this fact is. So what does it mean? Projection of the first components? Well, it's clear. I just forget again. So what are natural questions to ask? So these models, they were invented for, in fact, they were invented for energy levels of any. So these are just the energy levels of quantum systems. So of course, you have some very complicated quantum systems with very many degrees of freedom, but you want to know about its energy levels in some intervals. So in this language, it will be something like, what is, let's say, what is the number, well, we are on a circle, so in some arc. What is the number of eigenvalues in some arc? So let's say I. So what is the expected number of eigenvalues? I will use the notation hash I for number of particles in the So, what is this expectation? Well, in fact, you can see that this is just the integral of kn. Let's say the same. From what we proved. What is the expectation of some more complicated, let's consider something like this, some more complicated edge function, sum of f xi1 xik. So here xi1 xik are distinct particles, all possible choices, all possible choices of k distinct particles from x. So let me use the notation x for the moment. For the moment, it's fine. So x, this will be the notation I will use x is e to the I theta l. L at this moment from 1 to n. Soon enough will be. So all possible choices. So this is by what we formulated and then prove about this. Proof of this theorem is very nice exercise. We can do it next time. But I don't want to deprive you of pleasure. It's really proof is like 3 lines, but it is quite. If one of the things, once it's formulated, it's very simple, but maybe to guess, it was not so simple. It's called usually Determinantal. Okay, so this is equal to integral over the k dimension first, so we'll start with k f say the one k, but if you write e to the right, okay. Times precisely the determinant k theta I theta I k from 1 to k, and times the product. From 1 to 2. So this is the formula, which is just corollary of this definition. Does that make sense?
Sorry, corollary of what definition?
Oh, corollary, not of definition of proposition of the Determinantal theorem. It's just corollary. Determinantal theorem, because projection is this determinant. Maybe I should write K. So this determinant observes that the determinant is of matrix of size k, where k is just the number of variables. Observe that the only dependence on n is in the curve. That the formula as such does not depend on n. Does not depend on n. The only thing that depends is the curve. Does this make sense? So this is the very key point and step. So please ask me questions because this is just the very key step.
So X is the set of representative.
I can add X. Yes.
So
Please observe by the way the formula, this formula on the left side, on the left record, does not use any order on X. It is on purpose written in such a way that there is no order in it. Because there are all choices of k distinct parts. And the right side is also symmetric.
and F is any arbitrary.
Well, let's say to avoid, this is also a good question. Let's say to avoid questions of convergence, let's say just bounded function point. Let's say bounded function.
Bounded function
Of compact support. So that the sum on the left hand side is fine.
There is no need of regularity nor even mensurability.
No, Borel, of course.
We're on that.
Bounded Borel, of course. Bounded Borel, continuous.
Okay.
Continuous function.
And is there an ergodic way of looking at this statement?
There will be. So part of this is just. So far as this is just definition of this measure. This is just definition of my measure. It's just definition of my measure, but it's formulated in such a way that now I can very conveniently take n to infinity. Because please observe that this very simple, very direct definition is, how to explain myself? Well, I just reformulate. Is the only dependence on n is in the kernel Kn. And so, if I change my kernels in such a way that they converge to it, it makes every sense to suppose that the measures of the integration will also converge to limit. And this limit will then measure ergodic and so on, and many interesting properties from the neighborhood. Okay, now, okay. Let's continue here. So let me continue here. Yes. So let me just write. Yeah. Let me repeat this. And now let me observe, this is clear geometrically, that of course, well, I'm considering eigenvalue matrix. So there are n of them, and they're roughly equidistributed on the circle. They're roughly equidistributed on the circle. The circle is the circle. So, in order to obtain, if I look, how do I say, if I'm interested in what happens around my position, it is natural for me to expand by coefficient n. Right? The distance between neighboring eigenvalues is roughly 2 pi over n. So let me multiply. So let me consider theta to be 2 pi x over n. Right? Substituting here, I get, hoping that I didn't make a mistake, I get quite immediately. So please observe, there is one little nuance. So, of course, there is also change in the base measure. There's also change in the base measure. So I get n. So I get n Kn n over 2 pi. So this is my n over pi converges to, if I wrote it correctly, I should get psi pi x times x over pi x minus x.
That is the x tilde is the same relation.
Yes, yes, same. Correctly. There is one pipe that doesn't match. Just a minute. get confused. Just a moment. There's just some phi that doesn't match. I should be writing everything correctly, but not completely. Let me just write it like this now. There is something. Okay, I will return to it. The important part for me is this form. Is this form. So yes.
Yes, you need the 2 pi there, right?
Excuse me, second.
You need the 2 pi, right?
I do, right? Wait, I'm confused. Sorry, so it's thinking of lever has never been my strong.
Yes, but up to a 2 pi.
Let's write. Excuse me. Let's write. So okay, sine n plus 2 over 2 plus 2 pi x over n minus 2 pi x tilde over n. This is good. This is just goes to sine pi x minus x tilde. We're in great shape. Now, as regards this one, sine 2 pi x over n minus 2 pi x tilde over n, and there is an n. Yes, one red.
You need to divide by 2. Right, that's right.
That's exactly right.
Yeah.
So and then yes, there. One red. Yes, of course, excuse me, I'm saying something. Of course, it's completely correct, of course, because I have the same property. No, it's perfect. Yes. Because 2 pi is this 2 pi. The change of variables is 2 pi, but this 2 pi cancels with this 2 pi. So I'm sleepwalking, yes, of course, yes. No, it's perfect. It's perfect. So there is this n coming from change of variable, coming from expansion. Because really, please observe that I'm doing limit not in kernel as such, but in kernel times measure. So really, the canonical object is not the kernel, but in fact it is kernel times measure. So that's why I have this thing. So then there is this pi here, so there is this n, which is this n, and then excuse me, I had a moment of lighting. Yes, okay, and therefore we have arrived at the definition of the first main object of the course. So we have defined a measure on infinite subsets of the real line, measuring the infinite subsets of the real line. How it is defined? It's defined exactly like this, except here I do not torus to k, but arbitrary. Here, just to change notation, I do y1, y3. The determinant, so product is given. And the determinant is of this S, yi, yj. where S of LxDS is this kernel, the so-called signed kernel. So S y prime is precisely sine phi minus over pi. So this is this process called the sine process. Sine process. Sine. So now,
So
yes, yes.
just make it clear. So you're saying this depends a measure on the set of subsets of
infinite subsets of
incomparable.
countable infinite subsets of real one without accumulation.
Yes, and okay. And the way you compute the integral of the function f on that set is you choose a
Function f of special type. This function, observe this function of very special type. It's so-called additive function.
Sorry?
Excuse me. So the expectation is of a function of very special type. Yes? This is so-called additive statistics, but it does determine the measure. There are some subtleties. Please allow me to just skip them. I can explain them separately, but please allow me to say that in this setting, these expressions determine the measure.
Are these functions dense in some sense in a bigger space of observables?
Yes. So okay. If the question arises, I will answer it in more detail. Okay. I think I can erase this part. So now we just deal, as we will till the end of the course, we deal with infinite number of functions. So let me say. Okay. So what does it mean to? What does it mean to determine a measure? What does it mean to determine a measure? What does it mean to determine a measure on space of infinite subsets? Well, in this case, of line. Well, the natural random variables are precisely these ones. So number of particles in some interval. So I need to determine joint distributions of these numbers of particles. So I take, so now I'm not on the circle, but on the so I have some interval I1, IR, and I want to determine joint distribution of these numbers of particles in this interval, because this is precisely what it means to determine measure. These are parameters which determine this number. So this is tautologically what it means to determine. Okay, so I will determine these quantities in terms of their moments. And in fact, not in terms of their moments, but in terms of their factorial moments. So let us observe the joint factorial moment let's put that. It's precisely this additive function where n is the sum R1 plus and is the characteristic function, indicator function of I1 to the power of R1, indicator function of I2 to the power of R2, indicator function of L. So, indicator function of such a Q. Indicator function of such. Sum in this set. Sum is understood in this set. Excuse me, I don't need to write the computation. It's just a statement about observables.
So,
Yes?
what's the meaning of the power? Because these are not functions with 0 and errors.
No, just a second. F is a function on Rn. F is a function on Rn.
Okay.
F is a function on Rn.
So, okay, this is a Cartesian product.
Yes, very much. Yes, it is. It's just very simple, usual, and direct Cartesian product. That's quite precise. This is quite precise. This is just simple, usual Cartesian. So, at this point, we observe that knowing these integrals is exactly the same as knowing joint moments of these variables. Well, of course, knowing joint moments of random variables is not the same as knowing random variables. The joint distribution, but in many species it is. And so here, this is exactly so. Here, it's here, these determinants, they don't grow too fast. The moment problem is well posed, so it's okay. So here, these correlation functions determine the measure of uniqueness. I should point out that it is absolutely not obvious a priori that such measure exists. So here in this specific setting, we proved its existence directly as well, proved is maybe a bit too strong, but we essentially proved its existence directly. That is to say, by obtaining it as, limit of well-defined measures. Again, some argument would be needed to show that this limit is indeed well-defined, that the limit, there exists limit measure, but this can be done. Without much difficulty, in fact, just in a relatively straightforward way. And so that this measure exists. This measure exists.
Does these ideas go to other groups instead of the?
Actually, yes. Yes, there is.
To be compact.
Yes, they do, in fact. They do go to other groups, but it's very different theory. They do go to other groups, in fact, also, for example, yes, but it's very different.
In non-compact. I mean, SL2 or SLN. Determinantal matrices, for instance. Or it doesn't make sense.
So, but what would you consider? What would be so consider just eigenvalues? Then it is a little bit. There, it is possible to define measure in place of all matrices. I mean, I think it's somehow the examples I'm thinking about are more connected somehow with compact forms. I don't see any good example. I don't see a natural measure. I don't see a natural probability measure of SL M. Here it is very convenient, please observe that the measures of unitary groups are quite canonical. So they're canonical, but and also there is a projective limit. There is a projective limit. One can see, one can unite unitary groups into some sort of projective limit. One can project unitary matrix of size n onto unitary matrix of size n-1. There are ways of doing this. So there is a projective tower of measures, but if I'm not about the case, I don't see, unless it is some reformulation of a compact case, I don't see such stuff. Okay, so shall we take a 5-minute break and then I continue a little bit about the sign process? What is about this?
I don't know. For me, you could go on, but I don't know.
You decide. You decide.
For me, it's okay also.
Yeah.
Okay. So
Fine.
okay. So now very good. What do we do with this? What is my aim in this course? So let me formulate the main question and the main object of this course. So we will concentrate on the sign process, and the main object of study will be the characteristic polynomial of the matrix, or its analog to the sign process. So let me formulate first the main result. Proof, at least a sketch, I hope to explain in the course. Okay, so let me erase maybe here. The let me start with a little preamble. So if I consider again, I go back to my unitary matrix, which has n eigenvalues. Yes. So then it is clear. So I mentioned, I think, that the space, the kernel, which we started, was kernel of projection on the first n Fourier polynomials, n-1. Now it will be very clear that a Fourier polynomial of degree n-1, if it has n zeros, then it is identically zero. There is no secret.
Again?
A Fourier polynomial, Fourier ordinary standard of degree n-1,
Yes.
n-1, if it has n zeros, then it is identically zero. think there can be no doubt about this. I put it on to n-1 can only have n-1.
Okay.
So it is clear that this set of endpoints is a uniqueness set for my polynomial. And also any polynomial can be recovered from this uniqueness. So it's uniqueness set, but it's also minimal uniqueness. So if I remove one more point, then it's not uniqueness set. Okay. So now, for the sign process, the kernel that we wrote here, kx, here, well, s here it is also kernel of projection. It's kernel of projection on so-called Bailey linear space. Bailey linear space, which is space of functions, whose Fourier transform is supported in my design. Now, the question arises, what about relation between realizations and process and the perimeters? So, there is the fact theorem of Gauche, which says that almost every realization of this is a uniqueness set of space. Is a uniqueness set of coordinates. What does it mean, uniqueness set? It means that any such function is uniquely determined by its restriction onto this definition. The question arises, however, is it a minimal set? And the answer is somewhat unexpectedly that it is not. And so one of the main results of this course, which is a result of that, it is that realization without one particle, with one particle removed, is a complete minimal set.
Sorry, Stefan.
Just a second, let me
Yeah.
set. Yes.
First, I would need a clarification of what is the sign process for you.
It's measure. It's a measure. It's the measure. Sign process is a measure.
It's a measure on the space of
Substance. Yes.
Okay, on the space of substance. Okay, okay. So you think of it as a random variable on the space of this.
No, it's very it's measure.
It's a distribution area.
Yeah, or if you wish, yes,
Yeah.
it's random variable taking back to substance. It's a random substance. Yes.
Yes, and then it's
That's the
distribution
random
area.
substance. Random substance. Yes.
Okay, and by realization, okay.
This is this random substance. This one is this random substance.
And can you, so in this statement, is a unique set or it's a unique set? Yes.
Yes, yes, I'm not sure whether what is not clear.
Yeah, I wanted to understand the I want you to have a clear picture of the statement, of the meaning of the statement. So, okay, first part is clear, but when you say it's a uniqueness set for, I know you said, but can you say it in
Again, what does it mean uniqueness set? Yes, I can say it very much. It means that if a function in Penny space is zero in restriction to the set, then it is zero.
Okay.
Example of such set is Z. Example of completely minimal set is Z. So in fact, it's very classical theorem of Technical. That f of t, f is the sum of f of t, sum of t. Well, I write t minus k, but just to stress that that corresponds to by t minus k is equal to by t. So this k, I don't need to write it, I write it just to stress the shift. So this is theorem of Bufetov, which shows that Z is complete and minimal set for polynomial space. Right? Does it make sense? Yes. So this is the statement for my this is the statement for my relation analysis.
So you take any realization, you remove any points, and so that you get sets.
See, we need to do let's say
Okay.
let's say
I want because there are plenty of new concepts, so I feel the need to understand what you, and also mainly because I'm not so familiar with this. This is a bit away from classical ergodic theory, so I want to understand the concepts. So when you say complete minimal set, can you recall, you already said, but can you say again what?
again, that it is uniqueness and it is minimal set with this property.
Okay.
That it has this. Just please look here,
Yes.
because it's clear that every value has a role.
Yes.
So if it is a minimal set with this role, it's also clear that it is a set from which any function can be recovered. Okay. But here situation will be more difficult because there will not be such form, but still it is. it's to some extent C.
Can I give a question?
Yes.
What is for you that novel sub? It's like you're getting a collection of sets in your space A, E.
I'm not sure to which formula you're referring.
The numeral there. You're not. It's like going to the space of configurations.
This one?
Yeah.
Yes, the one that I erased.
Yeah, I want to understand what is the meaning of configuration.
Configuration is subset.
It's only subsets of the space.
Of R,
And,
yes.
yes, and that counts. Okay.
Yes.
Configuration.
Yes. Yes, it is just, yes, precisely. It is just, yes. And I'm just counting number of particles, yes.
But you are counting the configurations.
Number of particles, I'm counting particles.
Number of particles, okay.
Does it make sense?
No, because for example, I'm here in the archive trying to collect votes. So you say for almost every configuration, but you have a measure in the space of configurations.
That's exactly right. That's quite precise. Yes.
Okay. And your measure is going to be the one that you made for the same process.
That's exactly right. It is
Okay, that is the measure that you're going to have.
Yes. Yes.
Okay, no,
Okay,
I'm
so-
speaking. Sorry.
So let's do 5 minutes break.
Can I ask a question? When you say realization, for example, in this case, this is a realization.
Yes, a subset is a realization.
So in this case, it's C, the integrity is a realization. In this case that you have there, the cutoff,
That's right. That is a subset, yes.
that is a realization, no.
Excuse me, when it says realization in almost every subset according to this measure.
But in this case,
It means the set, excuse me, to put it formally, it means that the set of those subsets which with one particle removed become complete and minimal is a set of full measure.
okay, I'm not caring about this last sentence. I still try to figure out what is a realization.
No, the word realization in itself does not have any meaning. It's part of full sentence. I say it's how to say the full statement. I could formulate it more formally by saying that almost every subset has such property. So when I say realization, I mean almost every subset. Let me maybe write more.
And this doesn't have anything to do with realization, the hotel and but.
Can you say again, please?
This hotel because it doesn't have any relation with the realization.
But yes, the set Z behaves. The set Z is also a complete minimal set.
So, is this complete minimal sets going to be some give a description of the support of the measure or the place where the measure.
Well, exactly. The measure is supported.
Yes, this is the consequence.
This is the result.
Exactly. So I imagine there are many sets which do not satisfy this property.
Sure, of course,
Yeah.
of course. This is very special. Yes.
Okay.
Of course, this is very special. These are very special sets.
Okay.
Of course.
And so, so another question: if you take an arbitrary, so if you take a set. So not every set is going to be able to be the spectrum of a given matrix. So in general, there is some to be the spectrum of a matrix.
No, any subset of any n, no, but to the contrary, any n points of the unit circle are eigenvalues of the unit matrix.
Okay, yes, because you can construct them, but yes.
But here it is different because this measure in infinite case, it's different. The measure
takes
there is
the
no
format.
exactly. The measure is very special. So yes, exactly. So this is the whole point. So the measuring is supported on very special subsets. On very special. This is the whole one. The measure is supported on very special subsets. Yes.
So principle, I mean, every set would be a thing. I mean, the probability would be zero, but so every set.
Well, that's the whole point.
Yes.
What are probabilistic properties
Yes.
of their Gaussian distribution? There are many. There are several. There are many.
If for instance, the space of stochastic matrices or high-stochastic matrices, these are semi-groups. Well, the space of stochastic matrices is a semi-group. Probably, I don't know, maybe there is no natural measure that would play the role of our measure.
No, I don't see it. No, I don't see it. No, I don't see it. I don't see a natural measure on the space of markers and groups. I don't see a natural measure.
Okay.
No, in fact, no. This is very, very, very special.
Okay. Okay. So the mini course will be well, today is going to be about the just should control time because we are going to, well, I reserved an extra room, but next phase there will be not this problem. But today at 4:30, so in 20 minutes or so, we will have to.
We can continue next time. You decide. You told me.
Yeah.
You decide. So maybe we then continue next time. Sure.
Yeah, maybe because of the
Schedule. Yeah, of course.
and the recording, it will be complicated to move.
To move. Yeah, no, it's not.
Okay. Tomorrow there is no restriction to go on.
It's right.
Okay. So I don't know, maybe if you want to go on a bit more, since we don't have so much time.
No, that's okay. That's okay because it's not
Okay.
beginning. It doesn't make sense to begin here.
Okay. Okay, so can you give us an idea of what you're going to do next?
Proof.
Okay, this theorem.
Yes.
Okay,
We'll do the proof.
good, right.
Okay. Then you will state that theorem in more precise terms next time. Or...
It will still be precise, right?
When you need one particle removed,
Means with one particle, subset with one without one element.
So subset just without one element.
Yes.
And that element is just any element, you just remove any element.
Yes.
So after removing any element, you get a completely new set inside.
That's precisely right. Yes. That's what's written before.
It's a completely new set, but that's a function today.
That's exactly right. For the linear space, yes, it's the same word. Yes. This is all thing word.
Because
This is yeah. Thank you very much. Thank you very much. Yes. Almost every subset is within minimal set for the linear. Thank you very much. Yes, it was.
Sorry, because this is very interesting. I mean, this looks very powerful, very big theorem, because it has all these new concepts. Yeah, so we are absorbing them. This is it's in a paper in Archives 19, right?
Yes, that's right. It says, yeah, it's sign process and easy the facts.
Okay. Okay, and then you
Yes. So it is, yes, exactly. So one removes one more time, one obtains a complete additional set for the space.
And the proof is uses
There is the kind, if you want that mention with you.
the proof uses ergodic theory.
Yes.
Okay.
The proof really, yes. So what will be the key point will be the action of group of different models, as I wrote.
Okay.
As I wrote in the answer. Yes.
Yeah. Oh, very beautiful.
Okay, so we just let me just say one more thing. So just that the key object that we will study will be just this panel of characteristic polynomial. Will be just this panel of characteristic polynomials. So in fact, well, the characteristic polynomial is a polynomial whose zeros are precisely the particles of the process. So for example, just if I have just a circle and points, then I can have a polynomial which is 0 these endpoints. Here instead of polynomial, it will be entire function. It will be entire function with the zeros as points. So here it is. Product converges on principal value because so about this realization, one can think roughly as if it were the set. But it's not really, there are some differences, but very roughly it is. So obviously, this is analog of the Euler product with sign function. So and the principal, so inversion of principal value just with the Euler product with sign function. So and this will be the main object for us and the key point for us. So there will be the key point there will be a dynamic invariant element here. So the key point is that for different values of t's, these values they can have some large deviations, but also they can have some sufficient degree of independence. And by the way, this goes, so the scheme, it forms the scheme we call it this level, and also of eigenvalues and of that. So the scheme of the argument in this case follows their scheme is characteristic polynomial of random unitary matrix. So we will study this random entire function in the way in which these authors studied characteristic polynomial of random matrix. So let us continue next.
Okay, okay.
Thank you very much.
Thank you. So I don't know if someone wants to make. Well, I guess if someone wanted to make a question, do that.
From Zoom, any questions from Zoom?
No?
If not, then.
Okay, so maybe I'll start recording. Thank you so much, Sasha. We'll continue tomorrow.
Tomorrow, yes.
Yes.
This also gives us some time to think a bit about this and the.
So tomorrow at 3. Oi, Paulo.
Oi, Sasha.
Tudo bem?
Tudo ótimo.